Hello all, let's start section 1.8. Your section 1.8 is continuity. I will discuss in detail when a function can be continuous, how to know a function is continuous. We will go over all these lectures and we do few examples, actually a lot of examples. To understand continuity, because this is one of the topics that you will see even in Calculus 2. Calculus 3, it comes again and again and again. You should have a good understanding of what is continuity. If I give you a simple definition in a like 2-3 sentence, let's write first a simple definition, then I'm trying to give you a mathematical notation, how to know a function is continuous. Let's start with simple definition. I can say a curve, any curve, a curve is continuous if it has no holes. Let me put these ones kind of type of highlight for you. It has no holes, comma, breaks, or asymptote. Asymptote. Any function that has no hole in it, no break in it, or no asymptote in it, we call it continuous. These terms are actually holes, break, asymptote. It's the topic of algebra. It should be explained in the past for you in algebra classes, but don't worry, again, we will discuss it tonight. What does it mean, no holes? What does it mean, no break? What does it mean, asymptote? I'll show all graphs for you. This is a very simple definition of being a function being continuous, or even more easy, I can tell you, any function that when you graph like this, you are not picking up your pen from the page, it's a continuous function. When you pick your pen from the page and draw the second part of the graph, it's not continuous. Correct? In a very simple language. Now, let's make this definition a little bit more professional. A function is continuous at a point A at a point A, F. Now, I'll give you mathematical notation. That's the important part that you have to remember. These three criteria or conditions that if a function has these three criteria, it's continuous. If it doesn't have, it's not continuous. Number one, f of A is defined. F of A is defined. What does it mean? Remember, we discuss a lot. F of A is defined. It means point A should be on the graph. For example, this is a curve. This is A. A is on the graph, correct? Point A should be defined. Number 2, limit of f of x as x approaching to a should be equal to f of a. Remember this? I explained this rule actually as a direct substitution for you at the beginning of the limit, maybe in lecture number 2 of the limits. I explained to you there is a method, direct substitution, but when you can use, when f of x is equal f of a, it means a is in the domain of f. That's the meaning of a is in the domain of f. Number 3, limit of f of x as x approaching to a must exist. Remember the left side, right side, left hand, right hand limit? The limit must exist. When a limit can exist, when the limit of the left equals the limit of the right side, right? We explained this at the beginning when I start with limits, when I explained to you limits. When the limit of right side and the limit from left side, they are equal. For example, in this graph, when you come from the right and when you come from the left, both limits are going to the same point. It means they're equal. In this case, we say the limit exists. These 3 is actually the 3 conditions or criteria, or I can call it even test, when you check a function and you see if the function is continuous or not. Now, I'll do 3 easy examples for you based on the graph. I call these actually tutorial examples. Then slowly, we discuss more stuff and we go to more complicated kind of examples. Example number 1. Let me graph a function for you. A very simple function. This point is A. Correct? Let's see. I kind of zoom out a little bit my page because I want to show also this 3 criteria for you. And this example, let's check all 3 conditions. F of A is defined, correct? As f of A is defined, as A is on the graph, you see here I used an open circle, correct? It shows open circle in a graph. When you see like this, it means there is a hole in your graph, correct? There is a hole. Look at the definition, simple definition at the beginning that I write for you. A function is continuous if there is no hole, correct? But this function has a hole. It means test number 1, f of A is defined. No, you failed test 1. This graph failed test 1. Test number 2, I'll do all 3 tests on it. The limit of f of x equals f of A. The limit of, I put here numbers not in order. Let's name this one test 3. Let's name this one test 2. Limit of f of x must exist. Do we have a limit? Does the limit exist? You see, if you come from the right and if you come from the left to A, both of them is going to the same point. Of course, it's a hole there, right? But remember the definition of the limit. It's not necessary to have that point. You are going really close to that point. It means test number 2 passes. You say, yes, the limit of f of x exists. Test number 3, limit of f of x equals f of A. Correct? Do we have that? Do I have f of a? F of a is actually is not there. Let me put here another point for you. Maybe this is f of a. Because you see whole, you cannot plug in that number in the limit. It changes later. Now I'll explain it. An example for you. When there is a whole, it means this point is not there on the graph, correct? Maybe it's here. This is the limit. This is f of a. This is the limit. This is the f of a. The limit of f of x is not equal to f of a. Then here, no. Then I say this function is not continuous. It's discontinuous. And we call this one, let me write here, not continuous. At a. And we call this one removable discontinuity. Discontinuity. Removable discontinuity. Why removable? Because if you work a little bit on function, only one point can fill this hole. One point or one number can fill this hole. Later you will see how in the next example. That's why we call this one removable discontinuity. To explain it now more for you, I'll put another X. Show it in a fraction or in a function for you. For example, if you have f of x equals x squared minus 3 minus 9 over x, let's say minus 3. Remember this function from algebra? We call it rational function, correct? Rational function. Here, if you factor the numerator, you will end up with x minus 3 and x plus 3, right? Over x minus 3. And you see you can cancel x minus 3 with x minus 3. When you can cancel that, it means you have a whole. If you cannot cancel, it means you have an asymptote. Here, because you cancel, that's why we call it, it's a whole, right? And if I graph, actually your function becomes f of x equals x plus 3. Correct? But when you talk about the limit, you're looking to the domain of the actual function, not the new one, correct? X cannot take 3, correct? X plus 3 is a line, but if you look for that limit, you see the limit is not equal to the f of a. That's the thing that your algebra professor should explain before for you when you have a whole. When you cancel like this, you call it whole, correct? Let me do another example, example number 2. Let me see what I have here. Tonight, I'll use easy shapes. I know only this curve. This is point A. Again, our 3 conditions. Number 1. Number 1 was f of A is defined. What do you think? Is f of A is defined here? You see this closed circle at this end? It means f of A is defined. Then our function passes the first criteria. Number 2 is limit of f of x must exist. What do you think? Based on the lecture, that I did for you on limits is the limit of the left hand and the limit of the right hand is equal to each other. One of them goes up, one of them comes this way down. Do they meet each other at one point? Definitely no. Do you see the gap here or the jump, or some professors, they call it jump. I love to say it's a gap. There is a gap between these 2 points. They're not meeting at one point. It means the limit of f of x doesn't exist, because the limit of the left-hand side, if you come from the left this way, from the right, it gives you this value. And if you go from the left, it gives you this value, right? And these two numbers are not equal. Then the limit of f of x as x approaching to a does not exist. It means we failed test 2. Any function, believe me, any function, if it's given as a function, it's given as a graph. Apply these 3 tests on a function and you know if your function is continuous or not. It's that easy. Let's do test 3 on it. The limit of f of x, we do this test. The limit of f of x as x approaching to a should be equal to f of a. What do you think? Is the limit of f of x as x approaching to a equals to the f of a? F of a is here. The limit is approaching, actually it doesn't exist. The limit doesn't exist. Then it fails also test number 3. Then you can say this function is discontinuous. If you wanna give it a special name, it has a gap or a jump. I'm not sure they call it jump or not, but it has a gap. That's why it's discontinuous, correct? Now, another example, example 3. Let me graph another function for you. You know this dashed line, it's a vertical asymptote, right? For example, I have a graph like this and the other part of the graph like this. Let's do our 3 tests on this function. Number one, always ask yourself, f of a is defined. Is f of a is defined? Let me even put a point here. For example, this is f of a. This is a point. Is f of a is defined? If I have this point, yes, f of a is defined, right? Pass test 1. Test 2. Is the limit of f of x as x approaching, test number 2 is limit of f of x as x approaching to a exists? What will be your answer? When you're going from the right and when we are going from the left, is the limit of the right hand and the limit of the left hand are equal to each other? Look, both of them goes to positive infinity, right? Then it passes test 2. Test 3 is limit of f of x is equal as x approaching to a is equal to f of a. Your limit is infinity, but f of a is a number here. Look, for example, 2, 3, 5, 6, whatever is that one. Are they equal to each other? In this case, no. Here, they are not equal. Then you fail test 3. Then you say, my function is discontinuous at a. This function, discontinuous at a, and we call this one infinite discontinuity. Infinite discontinuity, correct? You see, I did 3 examples. And number 1, you fail test 1. And number 2, you fail test 2. And test 3 definitely, as if you fail test 2, you fail test 3 also. And example number 3, you pass number 1, number 2, but you fail number 3. You have this 3 options always. This is all about this continuity, right? How to find if a function is continuous or not. Now, let's do another example. Which example is a good example? For example, let's name this function h of x equals x squared minus 4 over x minus 2. They're asking you, oh, let's take a piecewise defined function, and here 4, here x, if x is not equal to 2, here x is equal to 2. They're checking, they're asking you to check if this piecewise defined function is continuous or not. Correct? First, copy your function number 1. You have h of x equals x squared minus 4 over x minus 2. X cannot take 2 because you see your denominator is x minus 2. If you make it equal to 0, x equal 2 as your vertical asymptote, right? X cannot take 2. But if you factor the numerator, which gives you x minus 2 times x plus 2 over x minus 2, these two cancels out. It means you have a whole, right? Now, test number 1. As f of a is defined here, as your f of a is defined, as f of a is defined, how to know? Look, when you cancel it, you end up with h of x equals x plus 2, right? Look at here your second condition. When x is 2, h of x is 4. If you plug in here 2, what is 2 plus 2? 4. It means if I graph this actually, this function for you, your function is something like 1, 2. If we graph x plus 2, right? It means you have a y-intercept at 0, 2. Your slope is 1 over 1. It'll be a line like this, something. At x equal to 3, 4. You see, 4 is on the graph. Then this function is defined. Pass test 1. Is the limit of f of x exist? You see, when you come from the right and when you go from the left, both of them is meeting at to each other, right? Then the limit exists. Test 3, is the limit from the right side and the left side are equal to each other? Yes. All 3 tests, yes. Then you can say this function is, this piecewise function is continuous, right? Now, let's make some more. F is continuous at every point, between an interval AB. between A and B, then f is continuous. Then f is continuous. Let's show it in a graph. For example, here A, here B. This is an interval AB. If your function is continuous at each point between AB, any number between AB. If the function is continuous, it means if you don't have hole between AB, if you don't have asymptote between AB, or if there is no gap between AB, in this case, you call this function as continuous. Remember, when I gave you this definition, that the limit of f of x as x approaching to a equals f of a, I told you that all polynomials, you can use direct substitution. All polynomial functions, they are continuous. And the easy understanding, when you put your pen, you don't pick your pen and you can graph a polynomial function. You don't pick your pen from the page up. It means you can graph it in one kind of move, right? Polynomial functions, all of them, they are continuous at any point. Polynomial, of course, you know the definition of polynomial. It means no radical is involved, no rational or fraction exponent, no denominator. We call those kind of expressions polynomial, right? All polynomial functions, they are continuous, correct? This lecture is a little bit long. Let's talk now a little bit about endpoint. Or endpoints. Let me again graph a function for you. Point B, point A. Now, is this function is continuous on which interval? I want to check. You see on the A, on the side A, at the endpoint A, your function is open, right? I used an open circle. It means I have to use a parentheses, A, comma. On the endpoint to the right, I used a closed circle. It means I will use a bracket here, right? AB. You know this from beginner algebra, right? When you use parentheses, when you use bracket. I want to now see if my function is continuous at the endpoints. Is the function is continuous here at this point? Is the function is continuous at this endpoint? Only on endpoints. Now, number one, or a star number one, I'll put a star. Continuity from left at point. You can name it A, B, or in general C, it doesn't matter, at point A. What is the condition? If the limit of f of x as x approaching to A from the left, because I told you continuity from the left. When you are approaching to your function from the left is equal to f of a, then your function is continuous at the endpoint from the left. Next one, continuity from right at point A. F, the limit of f of x, as x approaching to A from the right equals f of a, then you say my function is continuous on from the right at point A. Correct? Two more tests. Actually, you see your test is the same as limit of f of x equal f of a. I'll do an example. It's kind of proof, but not difficult. It's an easy proof. Let me show you how you check on a function. If this function is continuous, if this function is continuous at the right endpoint, left endpoint, correct? Example, prove f of x equals a square root of 16 minus x squared is continuous on closed interval of -4, 4. That means both sides you have closed circle, correct? They're asking you to prove that if this function is continuous in this closed interval. To do this proof, I'll do three things here. Number one, I will check in an open interval from -4 to 4 if my function is continuous. Number two, I will check if the limit of f of x as x approaching to 4 from the left equals to f of -4. I'll check this. I'm not sure it's equal or not. I didn't check yet, but I have to check this. Number three, I will check if the limit of f of x as x approaching to -4 from the right equals to f of, why I put here? Here you don't have negative, sorry, I put extra negative there. Equals to the f of equals f of -4. If I do this three tests, I can prove if my function is continuous in a closed interval from -4 to 4, right? Look here. When I am writing with number one, let's start with number one, this one. When I am writing limit of f of x as x approaching to a, right? It means actually in this example, the limit of square root of 16 minus x squared as x approaching to what? To a. Because your f of x is this function. The problem was f of x equals the square root of 16 minus x squared, right? I just replaced the f of x with the function. Now, let's think this way. F A is a number between -4 and 4. Any number between -4 and 4 on the number line, any number between -4 and 4. Let's think A is a number between -4 and 4, correct? If you plug in such a number, for example, let's say 3. If A is 3, is this limit exist? It means, can I plug 3 here? If I ask you the other night, I taught you actually direct substitution. If I have this limit, let me change the color because it's not part of problem. Again, remind you, if for example, I have limit of 16 minus x squared as x approaching to 3, can I use direct substitution here? Can I find easily the limit? The answer is yes, because 3 is in the domain of this function. How to find the domain? It's algebra. I repeat it for you. Again, I'm repeating how to find the domain or how to find the restriction. 16 minus x squared should be greater equal 0. Correct? It means negative x squared should be greater equal negative 16. It means x squared should be less than equal 16. It means x should be less than equal plus minus 4. That shows to you that 3 is in the domain of this function. It means the limit of square root of 16 minus x squared as x approaching to a is exists, right? And also, is this equal to the f of a? Instead of doing this limit, can I find the f of a? Are they the same, or f of 3, for example? Look, if you do limit, you plug in 3 here, 3 is square 9, 16 minus 9 gives you 7, square root of 7. If you go this way, plug in 3, it gives you again a square root of 7. It means your limit, here you go, your limit of f of x as x approaching to a equals to f of a. That was our goal to prove in an open interval. It means this one is correct. The function is continuous. Check number 2. I want to check. Let me change the color back to black. Maybe some of you don't like red. I want to check that the limit of f of x as x approaching to 4 from the left, it exists, or it's equal. Exist means it's equal to the f of 4. Why I choose this notation? Why I'm going to 4 from the left, going to -4 from the right, right? And maybe it's a question for you, how I set up that limit. Look, whatever the graph is, I don't care whatever the shape of the graph is. I'll just draw something like this for you. For example, here you have 4. This point is, let's say, this point is -4. Because I use bracket on both sides, closed interval, correct? When I set up my limit of f of x as x approaching to 4 from the left, it means when I'm coming this way, I cannot approach to 4 from the right side. There is no function here. Do you see a graph? No. That's why I set up this way my limit. Correct? Let's check it. What was f of x? The limit of f of x was square root of 16 minus x squared as x approaching to 4 from the left. As 4 is in the domain, yes. If you plug in, it gives you 16 minus 4 squared, which gives you square root of 0, which is what? 0. Also same time, if you look for the f of 4, your function is 16 minus x squared. Then f of 4 equals 16 minus 4 squared, which again gives you 0. It means you can write the limit of f of x as x approaching to 4 from the left equals to the f of 4. Yes, check. It means function is continuous, right? At the right endpoint. Also, last check, number 3, limit of f of x as x approaching to negative 4 from right. You see the reason. You can go from right to negative 4. You cannot come from the left to negative 4. There is no function here, right? That's why I set up my limit this way. It means limit of square root of 16 minus x squared as x approaching to negative 4 from the right. And if you plug in, it gives you 0 again. Here 0, here 0. The limit of the right hand, the limit of the left hand, they have the same limit. Correct? I did all 3 tests on this, or all 3 steps. It proves actually for me that my function, which was f of x equals a square root of 16 minus x squared, is continuous in a closed interval negative 4 to 4. Why in this interval? I test an open interval of negative 4 to 4. It gives me continuous. I test on the left endpoint. It is continuous. I left to the right endpoint. I tested right endpoint. It is continuous. Then the function in this closed interval is continuous. It was a kind of simple proof, not that difficult. If you just remember those 3 criteria that I gave you about continuity, correct? One more property, then I'll stop the lecture. Properties of limit. If you have two functions, f and g, and both of them is continuous at a point A. Continuous at a point. After this, I'm not writing like this at a point. Maybe I'll use this at a point A. Right? If you have two functions, f and g, and both of them is continuous at a point A, same point, then you can write these properties. F plus g is continuous at A. If you add these two functions, it's again continuous. F minus g is continuous at A. Number 3, f times g is continuous at A, right? Last, for operation, f over g is continuous at A, but be careful, g of A cannot be 0. Correct? Because if it's 0, it means you have a hole or an asymptote or a gap, correct? That's why hole or asymptote, not a gap, hole or asymptote. You can have these two because it will be a rational function. F over g is a rational function, correct? You can write these properties. Also, there is another interesting one that I don't have in my notes, but I saw in your book. They even talk about the composite function. They put a property like this for you. Again, if you are f and g, let's say this one, for example, number 5. Number 5 says f of g of x, your f of g of x equals to f gx, it can be also continuous at point A. Because f and g is continuous, then f of g is also continuous. Composite function, right? We practiced this before. This was all about 1.6. I'm sorry I didn't upload this section yet for you. It's a little bit late. It shouldn't be. It should be on the Canvas 2 days ago. I had a little bit problem with my recording tools here. That's why I fixed it. It took a little bit time. This was all about 1.6. And see you now. Next lecture will be chapter 2.